many of you actually sent in your posts with the city or village that you're from and your drinking water source. So that's very good. It's good to know that most of you know where your drinking water is coming from. Now what we're going to do is look at the flow chart that is used to show, the flow chart that we use to basically design water treatment plants. Okay, so these are what we call conventional water treatment plant. And what we have is basically two options. So we have a water that may be from a surface water body, or we have a water that is groundwater. Now, in general, these are again broad generalizations. In general, surface water body may be turbid. The water from the surface water body may be turbid. And in the groundwater case, the possibility is hard water. So we're going to look at each of these parameters. And I think in water treatment, I have given you some idea about what turbidity as well as hardness, but we'll go into some of the details about these parameters in a few slides. So before we go too far, the first thing you need to know is let's start with the conventional water treatment system. So the first thing we have is a water intake. You need to identify your source and you need to know where the water is coming from and how you will take it. You can have a water intake or you can have an infiltration well. In Kharagpur city, not in the campus, but in the city, they have what is called an infiltration well. So this is a river infiltration well where there are horizontal pipes. They may be either above the riverbed or below the riverbed. They're perforated pipes. They take in water from the river, or in some cases it is filtered through the riverbed. It depends on what system you can use. There are both systems are there. And this water comes to basically a structure that is on the river bank. And the case in the city of Kharagpur, they are getting extremely good quality water, which requires only disinfection. So that is one part. The second part is, let's say you have a turbid water. Let's say your water is muddy, it has a fair load of silt, and that's true for Hooghly and Kolkata. Okay, so over there you may have a water intake which has a perforated pipe, and the pipe is basically you have a suction pressure to pull in the water through the perforated pipe. So that is the first part. Then supposing the mud or silt load is fairly high, I can even include sand in it. So you can screen it. I've already mentioned that you have perforated pipes. So if the pipe is perforated, that's automatically providing screening. You can have other types of screening as well. You may have a pre-sedimentation tank. And in pre-sedimentation tank, I don't know if you remember the terms, discrete particles. So when you must have studied about Stokes Law and Newton's law, you have discrete particles. Now, discrete particles are defined as particles that settle by gravity. So this is a pre-sedimentation tank where discrete particles that are heavy enough can settle by gravity. So you get some amount of turbidity and TSS removal. So TSS is total suspended solids. So turbidity and TSS can be removed in this part. But very often it's not adequate. Sometimes you see that the water, even after settling, is somewhat muddy and the particles are not visible to the eye. So these particles which cause turbidity, but they are no longer visible to the eye, are called colloids. And we will look at that also in the subsequent slides. So turbidity and colloid removal is necessary, and for that we use coagulation and flocculation. Then we come to settling tank. Now, the whole objective of coagulation and flocculation is that these microscopic or submicron particles, okay, they are not visible. The individual particles are not visible to the eye. They are submicron in size, so less than 10 to the power minus 6 meters. Okay. Now, these particles have to be made to settle. One, because of their size, and two, because in some cases, if they're biological in nature and so on, they will not settle because their gravity is very close to the gravity of water. So, for various reasons, they will not settle on their own. And for that, to make that happen, we add a coagulant, we make them aggregate. So these particles which are repelling each other, I'll come to all those details later, they flock, and that is the FLOC. So the FLOC is the flock of particles that are aggregates of colloidal particles. They will then be made to settle. They will be given enough detention time and they will be made to settle in the settling tank. So that is for flock removal. And this flock has been formed in the flocculation basin. Beyond this, there may still be very, very small flock that remain in the water. Now, these are no longer colloidal particles, they are small flock and they have not settled within that 3-hour or 4-hour settling tank, 4-hour detention time. So for that, we take them to the filter. So this is generally a rapid sand filter. In a rapid sand filter, you get complete removal of turbidity, TSS, and flock. Okay. And finally, you store the water, and anytime, absolutely anytime, when you want to store water, it should be disinfected, and the disinfection process should be such that you have a long-term residual. So that long-term residual has to last for the amount of time that water takes from the treatment plant to the last consumer in the distribution system. So that can be 24 hours, that can be 48 hours. It should not be too long, but that residual should last for at least that period of time. And the main point over here is to prevent pathogens from growing in the storage tank or in the distribution network, and to remove them if possible. Then we come to hard groundwater. So you might say, what is hard groundwater? Hardness is associated with the presence of calcium and magnesium. So we define hardness as the concentration of calcium and magnesium, and we generally report it in milligrams per liter, but we will do some problems and you will have a better understanding of that. So the most common problem with groundwater, if it is good quality groundwater, the most common problem is hardness. And this hardness causes many problems. So one of the most common problems that we know about hardness is that many times when you wash your hands with soap and water, what happens? There is no froth. Okay. And you wonder what is wrong with the soap. We generally blame the soap and we generally say the soap is not good, right? Because it doesn't make froth or foam. The problem is not with the soap. The problem is with the water. The problem is with the hardness. So if the water contains high amounts of calcium and magnesium, it's not going to froth for various reasons. And you will often find in very hard waters, you will find that the soap, when you try to use it, forms what is called a white curd-like precipitate. So that is all, these are all indicators of high concentrations of calcium and magnesium. That is one very obvious problem associated with hardness. There is another very obvious problem associated with hardness, and that is if you use heating elements. For example, right now it's winter and most of you must be using either water heaters or hot rods for heating your bath water and so on, right? So what happens in that case? Now, after a fair bit of use, maybe a few months, maybe a year, you will find that there is a white crust on the surface of the heating element. The best way to do it is with a hot rod. If you use a hot rod, these are electrical rods that have a coil at the end, and you simply immerse the rod in water to heat it, to heat the water. And after a significant period of time, you will find that the rod has now changed color from a steelish color to white, really white. And that white comes from precipitates of calcium and magnesium. So over a period of time, you get a scale of calcium and magnesium on the hot rod or any other heating appliance. Those of you who use clothes irons, they also have a heating element inside it, your electric kettle, any heating appliance. Anytime you have water in contact with a heating element, you will get this problem if the water is hard. And then you have to use a dilute acid and remove that scale. We call it a scale. So that has to be removed. Calcium and magnesium are actually nutrients, and they are non-toxic. They don't cause any health problems, and the only problems that are associated with them are more of a practical nature. So this is the main problem in groundwater. Most groundwaters tend to have hardness issues. Another issue is the presence of gases, and you may also have low DO levels. Now, I often say this, that if you prefer refrigerated water to room temperature water, what is the difference in the water? The only difference in water is the temperature, right? So generally higher, you also know the relationship between DO and temperature. You know that as the temperature goes down, the DO level that is dissolved in water will go up. So that's why cold water in general tastes better than warm water. But because groundwater is not in contact with the atmosphere, therefore you often get lack of equilibrium and you get low DO levels in this groundwater. So when you taste the water, it may or may not taste very good. Okay. I've also mentioned that very often you find gases in them. So if it is at what we call suboxic levels, if it is not in equilibrium with the atmosphere, we call it suboxic conditions under the surface of the land. And in those conditions, you get several gases, CO2, H2S. These are the very common gases that are found in groundwater, especially deep groundwater. And because these are suboxic or maybe even zero DO, under those conditions, you will have reduced minerals. So Fe will be in the form of ferrous iron. Arsenic is associated with Fe. Now you also know that Fe2 has higher solubility than Fe3. Fe3 is practically insoluble if the pH is around 7. Fe3 has zero solubility practically. And arsenic is generally associated with iron, and especially in this part of, not this particular part of West Bengal, but the border areas of West Bengal are severely affected by arsenic in their groundwater. So these two are generally found together, and they are also very often in reduced form. Same thing with manganese. Actually, all three of them are generally found together, and they are, if the if the groundwater is in suboxic or anoxic conditions, you're going to find them in dissolved state and you're going to find them in reduced form. So this becomes, under certain conditions, it can be a problem. For example, arsenic is toxic. It's an extremely toxic metal. The current drinking water standard is 10 ppb. So when you bring the water to the surface, when you pump it out of the ground, the first thing that happens somewhat naturally, but you can increase the rate of aeration, is by providing air to the water. So the first process is aeration. And this is especially important for groundwater. I'll show you some examples of aerators. And the next one is softening. So we need to remove calcium and magnesium. And if I want to remove calcium and magnesium, we need to do two things. We have two options. We have lime and soda softening, and we have ion exchange. Ion means ION, ion exchange, because these two elements are found in ionic form. So it's Ca2 plus and magnesium 2 plus. So these ions can be removed by ion exchange processes. So we will take a look at that. And then we will come to filtration. Filtration can be done with or without rechlorination. Now, I already mentioned that you need filtration to remove turbidity, total suspended solids, and colloids. Now, one of the problems with filters, if the filtration rate is fairly slow, is that you get biological growth because bacteria, algae, fungi, all of them love surfaces. And you will find that the moment you have water and a surface, they will grow happily because there is sufficient nutrient available in the water for these microorganisms to grow. So many people prefer to pre-chlorinate the water before filtration. Some do it, some don't, but many do. Okay, so this chlorine is especially used to prevent biological growth on the filter media. Then we get disinfection and storage. That is the same as surface water. We want to store the water. We want to distribute the water. We want to make sure that the water that is stored and distributed is free of pathogens. So that is done by adding chlorine or ozone or UV radiation, depending on the point at which it is. So if it is the end of the water treatment plant, most people, maybe 99%, I don't know, are using chlorine. You can also use, let's say in your home treatment units, and home treatment units, you will find UV radiation. Almost all water treatment units that are what we call end of pipe or point of use treatment units, they are all based on UV radiation. Okay, so in all cases, the aim, the objective is to destroy pathogens, pathogens being disease-causing organisms. And you have to provide sufficient contact time to prevent these microbial organisms from entering the distribution system and regrowing in the distribution system. Because we are in an online mode, I'm going to give you a chance to raise your hand and ask your question. So you can unmute yourself and ask any question at any point in time. Okay, feel free to do that because, yeah, I can't see you, so that's a major problem. No questions up to this point? Okay. All right, so I've already mentioned most of these points. So here we have aeration. It's necessary for groundwaters that are anoxic. Anoxic means almost no DO. So dissolved oxygen levels are practically zero. And the question is, why is the dissolved oxygen zero? Because there's lack of equilibrium with the atmospheric oxygen. So that is the main reason why it's very poor. And the deeper the groundwater, the less DO you're likely to get. And whatever is there, the little amount that is there, if there is some amount of organic matter, then you will get a conversion of that by the bacteria and you will get even lower DO levels. Then when you do aeration, so let me show you what aeration is. What you're doing when you're aerating the water, you are oxidizing the reduced forms of ferrous iron to ferric iron, manganese iron to manganic iron. Same thing for arsenic contaminated water. It can be removed because it will precipitate. So there is something called co-precipitation of iron and arsenic, and just like they are found in nature together, when they are present in water, they will co-precipitate together. So that's one of the most effective methods that people have found for removing arsenic. Let me show you some graphics of aerators. This is an aerator. So all my photos are from the Gangtok water treatment plant. This is from a student who was here a long time back. So even in Kharagpur campus, even in our campus, we have the same cascade aerator, but it's a much, much smaller version because the water treatment plant here is a very small plant compared to, let's say, a city. A city like Gangtok probably has, I don't know how many lakhs to million population, and the plant would be much greater than what you, much bigger than what you have over here. So regardless, the principle remains the same. There is a central pipe. The pipe pulls in this case, it's lake water. The city actually gets lake water, and the lake water is very high quality water. In our case here in the campus, what you get is it comes from the river, and it's mostly river water, just like what I mentioned to you, just like the city. So here is a central pipe. The water comes in, it is distributed radially. And the steps are the ones that are called the cascade. So the steps are nothing else but to increase the interfacial area of the water in contact with air. So the greater the surface area of water, the greater the contact with atmospheric oxygen. So the greater amount of oxygen from, remember it's not at equilibrium. So the greater the surface area that you provide, the more oxygen from the air will enter water. So this is one method of doing that. Here is what is called a fountain type aerator. A fountain type aerator is very common. You have seen it. All fountains operate on the same principle. So this is the fountain when it's not in operation. You can see it's a circular set of main pipes, and they have nozzles. You can see the tiny nozzles. They're all facing upwards. So when the aerator is in operation, you can see what is happening. The water is thrown into the air in the form of small bubbles. I shouldn't use the word bubbles, they are droplets. So here we have droplets of water that are thrown into the air. And what is our technical objective? Our technical objective in all aeration processes is to maximize interfacial area. So the amount of surface area that the water is exposed to is going to, you want to maximize that, because the more surface area that is in contact with air, the better you will get in terms of DO levels. So this is what is done in most cases. Very, very common method. And the finer the size of the droplets, the better the results. So these are aerators. And then we come to, so I have shown you two, cascade and fountain aerators. There are also what is called tray aerators and diffusers. Now, tray aerators and diffusers both are very common in wastewater treatment, where aeration is again very important. So when we have activated sludge processes, we use these types of aerators, and I will show those graphics at that time. Okay, so in general, for water treatment, cascade and fountain are the most common ones. Then let's come to screening. Now, I've already mentioned to you that if you're taking water from a canal or from a river or from a flowing stream, you need to make sure that there are no large floating suspended solids. So it's very easy to put in a pipe which has a perforated end, and then when you pump the water out of the surface water body, then there is no damage to the pumps and to the other equipment that will be used. So that is the main point. So generally it's perforated pipes. This is a graphic from a wastewater treatment plant, and this is a large screen. So these kinds of large screens are used mainly in wastewater treatment plants. You can see the large materials accumulating on the back end, and this water is passing through these vertical bars. This is called a coarse vertical screen, and the water is, by gravity, it's coming into this channel. Okay, so that's all about aeration and screening. Now let's go to coagulation and flocculation. So now we have solids and suspensions. Now, in terms of solids, we have two types of, let's back up here. Let me back up here a little bit. You're all familiar with compounds in solution, right? So you have dissolved compounds in solution. Now, when you are dealing with colloidal particles, these are particles that are said to be in suspension. They are not solutions because they don't dissolve like a dissolved compound. So we say that these are particles in suspension. So we use the terms solids and suspensions. Now, particles and suspensions, or solids and suspensions. Within solids, you can have discrete particles and flocculating particles. You may be aware of all this, but I'm just going through it to make sure that you're all clear about these definitions. What is a discrete particle? Particles that do not change size, shape, and specific gravity over time. So the best example of a discrete particle is a sand grain. You look at sand, whether it's a riverbed, whether it's the beach, seafront, whatever it is, wherever you get the sand from. These are discrete particles. One, they're heavier than water. Two, they do not change size and shape over the time scale that we are looking at. And the specific gravity is also constant. So they're not going to change. Then we come to flocculating particles. We have size, shape, and specific gravity that changes over time. Now, what kind of particles are these? Most of them are either of biological origin, so they may be humic material, they may be natural organic matter, they may be bacteria, virus, protozoa. All these kinds are biological. We call them biological particles. Some of us call them biological particles. The problem with these biological particles is that they have varying size, shape, and specific gravity. That's one example. The second example is clay and silt. You know that clay and silt are very, very fine in nature. Now, even though they are much heavier than water, their small size and what is called electrostatic stabilization. So I'll come to that point later. But the small size and the negative charge on the surface makes them, depending on the environmental conditions, they either repel each other or they aggregate. Okay, so if they aggregate or coalesce, then obviously there is a change in size, shape, and specific gravity. They are modifying these three factors: size, shape, and specific gravity get modified depending on the environmental conditions. So depending on pH, depending on the concentration of particles, depending on so many other factors which we will come to later, they will change size, shape, and specific gravity. So these are called flocculating particles. Finally, what about suspensions? We have dilute suspensions and concentrated suspensions. These are two categories. So we have dilute suspensions are defined as suspensions where the concentration of particles are insufficient to displace water as the particle settles. So you can just imagine a cylinder filled with turbid water, and imagine that the turbid water is full of clay or silt. Okay. Now, when these particles come down, very slowly they will come down. Over a period of 24 hours, 48 hours, you will get a collection of sediment at the bottom. If these concentration of particles is insufficient to cause any displacement at the bottom, because they are so small and fine in nature, they will not be able to displace the water because the concentration is very low. Okay, so because it's very low, they are called dilute suspensions. And on the other hand, we have concentrated suspensions where as the particles settle, they create a layer at the bottom. There is a sufficient amount of particles in the water to create a thick enough layer at the bottom after they settle. And those are called concentrated suspensions. Now imagine what the examples are. The best example, the one that you can test for yourself, is take a cup of tea or milk and add some lemon to it. What will you get? You'll find that there is a concentration, you'll find particles aggregating and settling to the bottom. Okay, in both cases, particles will aggregate and settle to the bottom. And those are homogeneous suspensions, and they are relatively dilute suspensions. Wastewater, for those of you who may have worked in wastewater or so on, but in wastewater we have um, yeah, so in wastewater, the sludge is considered a concentrated suspension. So when we talk about activated sludge processes, we have a fairly high level of solids concentrations, very high level of particle concentration, and they form a mass at the bottom, which you might see in milk, because when you make paneer, which is exactly what I just mentioned, you heat the milk, add some lemon, and that's what you get. So you have a high concentration of particles, and those particles are biological in nature. They're carbohydrates, fats, and proteins. Yes, so that would be somewhere in between. It's not a very concentrated suspension, but it's more towards the concentrated suspension because you get a layer at the bottom. But wastewater is what we are interested in, so you'll find that that fits much better over here. So let me also give you another example. I've been talking about other things. We are here to talk about water treatment. So under drinking water conditions, in a drinking water treatment plant, even the most turbid water is considered a dilute suspension. So this is a dilute suspension that we are dealing with. And in wastewater treatment, we are dealing with concentrated suspensions. Okay. Now, this is a range of the particle sizes that we find in water treatment. So all the way from the smallest particles, which are viruses, to flock particles. These flock particles are exactly what you see after coagulation and flocculation. So let's take a look at these particles. Viruses have sizes anywhere from, this is in microns, so it's 5 nanometers to they've said 10 nanometers. That's not right. It's about, I would say, from 10 to 200 nanometers. Okay, so some virus particles are much bigger. Let's be sure about that. Yes. Just a second. If there is a question, ask now. Yeah. Anyway, this is exactly. Yeah, so let's just I'll change this at some point. So like I said, viruses can range from 10 nanometers to about 200 nanometers. Bacteria are generally defined as an average size of 1 micron, and they range from 0.2 to 2 microns. Then we have small colloids, and this is what we are going to be looking at. These are the 4 categories, including silt and clay, that we are going to look at. And anything less than 1 micron is considered to be colloidal. So the definition of a colloidal particle is that it is submicron, and whatever its specific gravity, whatever that may be. So for the biological particles, viruses, bacteria, even protozoa, if they are there, they have a specific gravity very close to water. And sand, silt, clay, very fine sand, silt and clay are considered small and large colloids depending on their size. And if they are less than 1 micron, they are considered colloidal particles. Soil particles, sand particles, if they are greater than 1 micron, they are considered to be discrete particles, because you can see it, when you take a sample of sand, add it to water, what will happen? It comes down very fast. Most coarse sand particles will settle very quickly within a few minutes. Soil, on the other hand, has a much wider range. So the particles that you see in soil tend to be partly colloidal. There will also be biological particles, and there will be sand-like particles as well. So it depends on the nature of the soil. You can have a very wide range. And finally, we come to floc particles. So the particles that we are creating in the water treatment plant have to be anywhere from, let's say, 100 to 2000 microns. And only then can they be removed by gravity settling. So gravitational settling is not working for these submicron particles. For could you please mute yourself? Somebody's mic is on. Please mute yourself. Yeah. Okay. So then we have these stable particles. Now these stable, let's come to the next point. What is the meaning of the word stable particles? I will we'll come to this point again. Lost that. Okay, before we come to more details about stable particles, I need to back up a little bit. There is some disorganization over here. So when I said you have 2 types of particles, discrete particles and flocculating particles. How can you remove the discrete particles? So anything that is greater than 1 micron and heavier than water will be removed by gravity alone. So that is what we call sedimentation or settling tanks. So sedimentation or settling tanks can be used for floc removal, but this floc removal is after it has been coagulated. These detention times can be very wide. It all depends on the nature of the material that you are trying to remove. So the detention time can be as less as 1 hour all the way to 10 hours. And when you are dealing with flocculating particles, there is no limit to how long you can provide detention time. After all, as you increase detention time, the cost of making the tank will automatically increase. So if cost is not a factor, we can go on for much longer detention times. The most common detention time, in the absence of any other information, is 3 to 4 hours. So 3 to 4 hours is the most common detention time, but it can be less, it can be more. We'll come back to, or should I do this? Now, I think most of you are fully aware of Newton's law and Stokes law, correct? A few hands. Anyone who wants to say, I've never studied Stokes law? No one, right? So I know that you've all studied Stokes law way back in high school, so you need to refresh your memories about that. And I won't go through the derivation. It's there practically in every book. I'll just show you a couple of things. So this is the first equation. This is based on Newton's law. The derivation is in the textbook. If you have any problems, you can refer to, like I said, it's there in almost every water or wastewater treatment textbook and in environmental engineering textbooks. All of them have this derivation. So starting from the first principles, you can derive Newton's law. Vs is the settling velocity. Rho p is the density of the particle. Rho w is the density of water. G is gravitational acceleration. dp is the diameter of the particle. Cd is the drag coefficient, and this drag coefficient is based on Reynolds number, and Reynolds number, as you know, is based on flow conditions. So if you have laminar flow and a Reynolds number that is less than 0.2, then your CD equation is equal to 24 by Reynolds number. If your flow, let's take the other extreme, if the flow can be considered turbulent, which means Reynolds number from 1000 to 2 times 10 to the power 5. And at that point, CD is equal to 0.445. Now, this is for turbulent flow. So you can see we can also I need to mention over here, some textbooks say Reynolds number less than 1. Other textbooks use Reynolds number less than 0.2. Either way, it's not a big difference. Anything less than 1 or 0.2 is considered laminar. What about the range in between? In the middle, we have transitional flow, and CD is equal to 24 by RE plus 3 by root RE plus 0.34. And you know that Reynolds number is the ratio of inertial forces to viscous forces. So you have phi. Phi is the sphericity of the particle. Rho W is the density of water. Vs is this should be small v, not capital V. This is the settling velocity. I'm sorry. Whoa. I'm sorry. This is the volume of the, no. This is the volume of the particle. It should be Vp. Yeah. Yeah, Vp is the volume of the particle. This should not be Vs, it should be Vp. गड़बड़ है यहाँ. We'll have to, I'll check this and come back to you. And then we have the diameter of the particle. And divide that by the dynamic viscosity, which is mu. Let me back up here. This should be small v. It is Vs, okay, the settling velocity. So this is where we are. This is small v. Just make a note of that. Okay, and phi, like I said, is the sphericity of the particle, and that means how much does it deviate from a perfect sphere. So if it is a perfect sphere, then the value of phi is 1, and it ranges from 0 to 1. So the greater the irregular shape of the particle, then it is less than 1 tending towards 0. So a perfect sphere has a sphericity of 1 and a shape factor of 6. We're not going to go into any details here. It's all there in the book. For laminar conditions and particles that are perfect spheres, phi is equal to 1, CD is equal to 24 by Reynolds number, and we get Stokes law. So this is our settling velocity for laminar conditions and perfect spheres. So this is what you have. And there is a practice problem for you. I will give you 5 minutes later on. Give me another 5 minutes and then we'll go to this. Yeah. So then we come to coagulation, flocculation. So what is coagulation and flocculation? Like I said, it is for the turbidity removal and for suspended solvents removal. So our design objective is removal of colloidal particles. And as I said, colloidal particles are any particles that are less than 1 micron in size. So you can remove bacteria, soil, sand, clay, silt, all these particles can be removed. Those of you who have access to river water, especially people in the Kolkata region, you can always go and take a sample of the river water and you will find that it's quite muddy. And that muddy nature and the lack of settling, if you take this water, put it on, put it in a glass bottle or just a container, what you will find is it takes a long time for this water to become clear. So these are colloidal particles, and like I said, they don't settle on their own. You need to destabilize them. So let me just explain what stable particles are, and then we can stop for a few minutes. So this is the first thing. We want to remove these sub-micron sized particles. Point number one. In the process of removing these colloidal particles, you may get removal of natural organic matter, heavy metals, pesticides, and so on. So that's an objective. That's not our main objective, but that happens, and it's very useful as well, because the best way to say it is that coagulation is a very crude but effective process. It will not give you 90% or 99% removal, but it gives you what is called a broad spectrum removal. So you get removal of anything and everything that's there in water, and the efficiency can be about 50 to 70%. Okay, so sometimes it's sufficient for drinking water treatment. Then we come to the next point. And when I was talking about particles, I said these particles are stable. These colloidal particles tend to be stable. What is the meaning of stable? Stable means these particles are present in water, and assume that it's a silt or clay particle. So if it's a silt or clay particle, under pH conditions close to 7, it's going to be completely negatively charged. So this is the surface charge. They are all negatively charged. Now, if every particle in the water is negatively charged, but the water itself is electroneutral, right? So you will get repulsion. So you will get electrostatic repulsion. These particles, because of their negative charges, will never come close together. And because they are so small and there are positive charges around them, they will, first thing is they won't come close together, and two, they are so small in size, they will not settle by gravity. So you have dilute solution in nature. This is very common in river waters. You have low ionic strength. They are freshwater systems. We generally go for freshwater for drinking purposes. So these are dilute solutions, or suspensions, I should say. But you have to remember that in drinking water systems, you can call it a solution or a suspension. It doesn't matter, because both are present. You have dissolved compounds and you have particles. Both of them coexist. Okay, and we are dealing with particles. We're not dealing, so dilute solution is the right word, because we are dealing with ionic strength. And when we talk about cations and anions, we're dealing with solution, because it's not applicable to particles, it's applicable to the other ions in solution. Now, because the particles are negatively charged, positive ions, cations, will aggregate to the surface of these negatively charged particles. But because it's dilute, the particles are physically far apart from each other, and there is no attraction because they are all like charges. So because of the net repulsion and the physical distance, they're not going to come together. They will remain exactly where they are in that volume of water. So people have actually done studies with lake waters, with high quality lake waters, just like the lakes in Gangtok or any other Himalayan or lakes in the Alps and so on. So what they find is that despite the very low concentration of particles, these particles never settle. Months and years will go by and these particles will remain exactly where they are. No movement at all. So that's why we call them stable. You can say stable in solution or stable in suspension. And so how do we destabilize them? Because they give a certain amount of turbidity to water, and we don't want to drink water which has these particles in it. So we add coagulants. Now, if you add a coagulant like alum or ferric chloride, what will happen? Alum will give you aluminum 3 plus, ferric chloride will give you Fe 3 plus. Now you have both cations, you're adding a salt, so you have both cations and anions in water. The cations will gravitate towards the negative charge on the surface of the particle, so you will get a very high concentration of positive charges around the particle. Same thing on all the other particles. So as much as you add, you will neutralize the negative surface charge of the particle. Once that surface charge is neutral, they will come together, they will form aggregates. These aggregates at some point will become heavier than water, and that will be sufficient to allow them to settle by gravity. So addition of coagulants to solution, and that will also result in high ionic strength because you're adding a salt, so the ionic strength automatically will rise and these particles will come together, form what we call a flock, and the flock will settle by gravity. So this is the natural state. The stable particles in natural systems are stable, they don't move, they remain where they are. And that's because of mutual or electrostatic repulsion between all negatively charged particles. And they will remain suspended in solution. Now, no aggregation, like I said, is possible, and we add a coagulant to get the results we want. So here we have, in the lab, we do what are called jar tests. So when we do a jar test, what we do is we take 6 beakers. Normally, coagulation apparatus has 6 beakers, generally 1.5 liter, 2 liter beakers. We take 1 liter solutions, we add different amounts of coagulant. So this is 0 for comparison. This is the starting solution. This is actual river water. This is the river water that we get in campus. This is how turbid it is. It's not toxic. There are no problems with it. It just has a high burden of silt and clay particles. So you can see it's got a fairly turbid look. This is what it looks originally. You add small doses of coagulant. You mix it rapidly for 2 minutes at a speed of 100 RPM. RPM means the number of and then we have flocculation for 15 minutes. Now, the difference between rapid mix and flocculation is the speed of mixing. So the speed of mixing initially for 2 minutes is 100 RPM. And after the first step, you come to the gentle mixing for 15 minutes at 35 RPM. And then you allow settling for minimum 1 hour. Minimum time is 1 hour. You can go to, like I said, we've done it for 24 hours, we've done it for 48 hours. So there's no limit to the maximum, literally. But remember that in practice, when you're designing a process, there is obviously a limit in terms of your budget. You can't have a infinite budget. So it all comes down to what you can afford to design in terms of a tank. So most people design for a settling time of 3 hours, and like I said, the minimum is 1 hour. And then in the lab, we filter it through filter paper. But in the water treatment plant, we use rapid sand filters. I will talk about that in the next, perhaps in the next class or in the next few slides. So in the jar tests, as you add more and more coagulant, you can see that you get some level of settling. You can see the settled material at the bottom. You can see that the turbidity is going down from here to here to here. But then at 10 milligrams per liter, it went up. And then at 20, it's almost drinking water quality. You will probably look at this water and say, it's okay, it's not so bad, right? This is typical of jar test results. You get what is called a minima at this point when the charge on the particles is completely neutralized. As you add more particles, you get restabilization of these particles, and then you get what is called sweep flock formation. So when you add too much of the coagulant, you get precipitates. And when these precipitates start settling, because aluminum and iron both are heavier than water, they will form hydroxides, and these hydroxide precipitates of aluminum and iron will start settling, and when they start settling, whatever comes in their way will sit at the bottom of the beaker. So this is removal by what we call sweep flock formation. So I think I've covered all that. These are the results. So one of the students, BTech student, he did these jar tests long time back, and these are the turbidity and UVA. UVA is UV absorbance at 254 nanometers, and this is used as what we call a surrogate parameter for natural organic matter. So we have organic material that is present in water and which can contribute to turbidity along with silt and clay and bacteria and virus and all of that. So it's a gross parameter just like turbidity, but it represents natural organic matter, more of a dissolved, dissolved set of compounds. So we have turbidity and UVA, and this is the alum dose. Alum is the most common coagulant that we use in drinking water. So you can see at 0, obviously the turbidity is fairly high, it's about 13. Then you come to 2 milligrams per liter, then 5, 10, and 20. And you can see between 10 and 20, there's very little difference. And these are 2 sets of results. You can see the alum dose in a different water sample. It has gone up by an order of magnitude. So instead of 5, we have 50, 100, 150, and so on. In terms of UVA, now I've used a term here called enhanced coagulation. Enhanced coagulation means you are optimizing not just for turbidity removal, but for UVA as well, and UVA representing natural organic matter. Natural organic matter is dissolved organic matter. And all of that will be removed at more or less the same doses. So if you take the first sample, November sample, this is post-monsoon, and March is further down. Actually, we don't have any post-monsoon sample. That would have been interesting. But regardless, you can see there is a small difference between the 2 samples. In November, the best results are 20. So if I want to achieve 2 purposes, I want to remove turbidity as well as UV absorbance, then 20 is the answer. If I want to remove only turbidity, then 10 milligrams per liter is sufficient. In both cases, 10 and 20, the minimum turbidity achieved was 2 NTU. The drinking water standard today is 1 NTU. Okay, so it's not sufficient. Same thing over here in March, the water quality was much poorer, and you can see that the minimum turbidity was about 10 NTU, and it follows the dissolved and suspended solids, both of them are more or less equal, very little difference. And the requirement, the minimum would be somewhere around here, 60, between 60 and 70. Okay, so that's kind of typical. And there is a small drop in pH depending on the nature of the water. Um, any questions at this point? So, flocculation and mixing is the second part of the process, and that is where you do the rapid mixing. So the detention time in practice in a water treatment plant is about half a minute to 1 minute. And these days, there are no rapid mix tanks. Nowadays, what they do is they inject the coagulant directly into the main pipe. So you have the main pipe bringing in the water, and this coagulant is directly injected into the pipe. So that has become very common. And the detention time becomes even less than this. And there is no separate tank for this. So it minimizes cost and you get the same results, maybe even better. Then we have slow mixing. Slow mixing is essential for physically bringing the particles together, because remember that it's a problem only because the particle concentration is very low. So you have to mix it gently. Again, like I said, you can try it with milk or tea. These are simple experiments that you can do for yourself in the kitchen just to partly amuse yourself, and you can actually see it happening before your eyes. When you add lemon to warm milk and tea, you know what happens. They are both colloidal suspensions and you can see the particles. Remember what tea is. Tea is NOM. It's natural organic matter. It's got tannins and lignins. Tannins and lignins are acidic compounds. They're natural organic. This is what we call natural organic matter. And the moment you add lemon, it acts like a coagulant and you get flock formation and settling of the flock at the bottom. And those of you who know how paneer is made, chena or paneer, whatever you call it, the same principle works for milk. Milk is also a colloidal suspension. It's a homogenized colloidal suspension. So whenever you add acid to it, it works in the same way. It will form flock and settle at the bottom. And that flock is what we eat as paneer. So that is, these are simple practical examples that you can do in your kitchen. So if you don't do it, so you can try it in both cases. If you mix it gently, very gently, you will find that the flock settles, it comes together. But generally what I find in milk and tea is that it's better not to do any mixing because the suspension is heavy enough, and it's better not to mix it at all because it breaks up. So in drinking water treatment, our suspensions are much more dilute than both of these suspensions. So drinking water systems in general have much better quality, and you need very, very slow mixing. So when you go to a water treatment plant, you will find that the speed at which they are mixing is extremely slow. And the only reason is to cause particles to collide with each other. So when they collide with each other, they will form aggregates, and that is useful. So this optimum, now two optima have to be determined. One is the coagulant dose and the second is the speed. But because it's kind of tedious to do these experiments, we generally make assumptions and we do our design based on these assumptions. So I'll come to, okay, let's take a little practical break. I will ask you to solve at least one of these problems. Um, some of you can take 1 millimeter. Please read this problem. So I'll just read it out. Determine the settling velocity of sand particles with diameters of 1 millimeter, 1 micron, 10 microns, and 0.1 micron. The specific gravity, the assumptions are given here. Specific gravity of sand is 2.65. Assume the particles are absolute spheres, perfect spheres. Water temperature is 20 degrees centigrade. Density of water is 998 kilograms per cubic meter. Dynamic viscosity, which is mu, is 1 times 10 to the minus 3 Newton second per square meter. So you will have to determine Reynolds number for each particle and determine the flow regime, and then decide whether Newton's law applies or Stokes law applies. Okay, so I would suggest that each one of you take a different diameter. So there's quite a few of them, quite a few students here. How many do we have? Yeah, so we have a good number, and you can all decide. I'll let it be random. Yeah. Um, I'll give you 5 minutes. Each one of you should solve at least one. So don't go for the first one. Someone should take the second, others should take the third, and so on, right? If you get an answer, just raise your hand and let me know. No answers? Just make this change. This is the velocity. I'm waiting for at least 2 to 3 answers. There are 4 problems. For D is equal to 1 millimeter, Reynolds number is 0.011 078. Okay. Anyone else?
Ma'am, could you show the question again?
Make a note of the question.
Ma'am, also could previous slide one.
Uh, is this the one you want?
Yes, ma'am.
Okay. For D is equal to 10 microns, your answer, your settling velocity is 0.88 times 10 to the minus 10. What are the units? 10 microns, what are the units? Meters per second. Could you check your 10 to the power minus 10? Shraman. Yeah, Shraman Pal. Please check whether it's 10 to the power minus 10 or some other number. What is your Reynolds number? Reynolds number is too small. That's too small, too small. 10 to the power, oh boy. The next one went even further down. No, go up.
Ma'am, how will it go? Because the multiplication is in 10 to the power minus, not plus power.
Right. So 1 micron is 10 to the power minus 6 meters. Yeah, your Reynolds number was something is really wrong here. It can't be that low. It can't be that low. Will somebody do it for 10 millimeters? Is 10 millimeter there in the question? Okay, so I asked you 1 millimeter. Somebody do it for 10 millimeters. One micron. 10 microns, you should have gotten it right. Your Reynolds value, I'll tell you my Reynolds value for 10 microns. For 10 microns, my Reynolds number is 8.95 times 10 to the minus 4. And the settling velocity, it's a laminar flow regime, so the settling velocity is 8.98 times 10 to the minus 5 meters per second. Okay, let's move to the next topic. So I will leave you to sort it out. You're all, I think you're right with the digits, with the numbers, but you're off by orders of magnitude. So please check your units. Make sure grams, kilograms, newtons, all that is working out, because the only mistake I see in the answers is the order of magnitude. 10 to the power minus 11 should be 10 to the power minus 5. And 10 to the power Adrija, 10 to the power minus 21 for Reynolds number should be your diameter. So that should be 10 to the power minus 8 in your case. Okay, so you're all off by a order of magnitude. For 10 millimeters, so for 10 millimeters, VS, okay, for 10 millimeters, Newton's law is no longer applicable. It's too large. Just look at 10 millimeters. That's 1 centimeter, right? So Newton's law breaks down. You cannot have a negative, your Reynolds number is way too high. Just think in terms of what is Reynolds number. Reynolds number is inertial forces divided by viscous forces. And when you're dealing with, let's say, something that's 10 millimeters, 10 millimeters means it's a large pebble. So that pebble in water, just imagine how it behaves. You put a pebble in water, it'll come down right away, right? So inertia behaves, rules. So you can't have a negative order of magnitude. So it has to be positive. I have +5. So just check your numbers. You're all off by orders of magnitude, nothing else. Check your units, okay? Whew. All right, let's continue with the remaining part of this topic. All right. So up to this point, I've been talking about clarification and flocculation or coagulation flocculation. Now, how does it happen in practice? So this is the most common design process, or what should I say? This is the most common process that we use in drinking water treatment. These days, it's practically universal. These are called clariflocculators. Stands for the clarification part. Clarification is the word we use for the removal of particles from the uh, volume. So this process where the colloidal particles have been coagulated and they're given time to settle. So that settling process is called clarification. Okay, and then you get the sediment layer at the bottom. Now this is what it looks like in reality. So here we have our clariflocculators. This is an aerial view. What you see over here is there are two tanks, literally. So the water comes in at the center, and all around the tank you have what is called a collection trough. So let us take a look at the schematic. The water comes in at the center. It is radially distributing itself in all directions. This is a circular tank. So what you're looking at is a cross section of a circular tank. And there are walls. So there is, just look at this. There is a wall kind of thing, but this wall is open at the bottom. So the water comes in at the center, and so it's coming in here. It moves into this part of the tank. The wall is not all the way to the bottom of the tank. It's open at the bottom, and there are paddles inside this. So these paddles are rotating very, very, very slowly, a few millimeters per minute, you might say. Okay, so it's a very, very gentle process, and the only thing that this wall does, it's literally like a suspended wall. What this wall does is it separates the flocculation tank from the settling tank. This area is the settling tank, and the volume in the center is the flocculation part of it. So the central shaft is moving at the same rate. RPM is the same, but as you move away from the center, the velocity is increasing. Yes. The velocity here will be much less as the tip of the, now there are two things, I haven't explained this. So the velocity of the water here is maximum, and as you go further away to the edge of the tank, to the periphery of the tank, you will get less velocity, but that's not what we are interested in. We want the particles in the water to start settling. Okay, so in this whole thing, they have to start settling. Now, the shaft is the same. The paddles are mounted in the center. So remember that the RPM is very, very low. And at the bottom of this shaft is what is called a scraper. This is the central scraper, and there's a sludge hopper over here. This scraper has either rubber or wooden arms and so on. Now, wait a second. This is the scraper arm, and the scrapers, you can think about the scrapers that we use for cleaning glass surfaces. Some of these may be of those type, but maybe other types as well. So this scraper arm has a bunch of scrapers. You can see 3 shown in this schematic. They are all at an angle, and you can see that the floor of the tank is also angled to the center, and the hopper is in the center. So when this entire shaft is rotating, what you get is What you get is whatever has settled over here at the bottom is going to be automatically pushed into the hopper. So this is all happening over here, and that's how you get two processes in the same tank. So here you get the not colloid formation, you will get floc formation, and here you will get sludge formation. So all this floc that has formed here in this zone will settle in the remaining part of the tank. And the clarified water will overflow into the collection channel. So here is the collection channel. So that's all. Okay. Then we come to filtration. Now, filtration, like I said, is for the removal of flocculated particles that cannot be removed by settling. Remember what I said, that the floc has to be big enough to settle by gravity. So if it is big enough, it will settle by gravity, and that has been removed. But there will be other flocculated particles that are not big enough and they cannot be removed by gravity. So we have two options. For them, we have rapid sand filters and slow sand filters. Slow sand filters used to be very popular. They have low input output. Throughput means what comes in, what goes out, and they're generally equal. So the throughput is much less. In a slow sand filter, in a rapid sand filter, the throughput is much higher. Adsorption is another mechanism for particle removal. So other than the simple filtration, now simple filtration means the particles that are there are going to be caught in the pores and removed through the filter. And then we have adsorption, which is another mechanism. Adsorption means the particles will stick to the filter grains. Okay, so that is another one. Now, let me show you something before we go too far. So this is a slow sand filter. You have a layer of gravel resting on what we call an under drainage system. And above the gravel layer is a sand layer. And above the sand layer is river water in this case. So the river water is coming in. You have raw water, and because this river water has organic material, so you have humic material, you have natural organic matter. This organic material which is there in the water is sufficient for bacteria to grow, and if the tank or filter is open to the sun, then you will get algal growth as well. So what is generally recommended is that there should be a roof over the slow sand filters, because if you don't have a roof and there is exposure to light, you will get algal growth, and that will contribute to the burden of organic matter. So if assuming there is a roof at the top, you will get bacterial activity, and that bacterial activity is actually useful because the organic matter in the river water will be destroyed by the bacteria that grow at the top. Now this top will form what is called a slime layer, slime because of the bacterial growth. So this bacteria that's growing at the top will form this slime layer, and it will add to the filtration of the, it will add to the efficiency of the filter. But after a good amount of time, maybe a few months, maybe a few years, you will get sufficient buildup of this slime layer, and you have to remove it manually. So that has to be done periodically, depending on the quality of the input water, inlet water, and depending on the concentration of organic matter. Because if the organic matter concentration is high, then the bacterial level will also be high, and you will get clogging of the filter at the top. So that manual cleaning is the biggest problem with this filter. Otherwise, it's quite efficient. And then after it has been filtered, it's taken for disinfection. Now, what about rapid sand filters? In rapid sand filters, you see a different phenomenon. So here is a rapid sand filter. You can see that the design is a little more complicated compared to a slow sand filter. You have your under drainage system. This is our under drain system, followed by a gravel layer on top of it. And on top of that, you have a sand layer. And then above the sand layer, this is the water column and this is the freeboard. Okay, so the freeboard is what is used to apply some, how do I put this? No, the water level is maintained above the sand filter so that there is some hydrostatic pressure to push the water through the filter. Okay, and the sand, in this particular schematic, we are showing only one type of media, which is the sand, but you can have multimedia filters as well. I'm not going to go there for the purposes of this class. A single media filter is sufficient. And then how does it work? Okay, so you can see various valves are shown over here. There is an influent valve. Influent means what is the feed water. So your river water or your lake, pond, whatever your source of water is coming in over here. There is filling up of the filter, and this is your actual water level during the filtration process. Okay, so this water is, because of the hydrostatic pressure, it will be pushed through the filter, and during operation, A is open and your clarified water, which is coming out at the bottom, is, that's your effluent in this particular schematic, and A and B both are open. So while the filter is operating, all other C, D and E are closed. A and B are open. There comes a point after a few hours in a rapid sand filter, depending on the capacity of the filter, depending on the filtration rate, it may be hours or days, maximum 1 or 2 days. But in general, what I know in practice is that it's never more than 24 hours. Even in campus, they have a backwashing. The next step is backwashing, and this backwashing rate is every 6 hours, sometimes even less than that. Sometimes they do it every 2-3 hours. Okay, they wash the filters. So what happens is that depending on the quality of the input water, if the input water, let's say in the monsoon season or even in the post-monsoon season, you have poor quality water, means high turbidity, high organic matter, all of that. Now, if the input water has poor quality, this filter will clog very easily and it needs to be cleaned. And for cleaning, the first thing is you shut off the input. You close B because the output is no longer meeting the standard. So there are 2 points which I'm not going to add over here, but there are 2 points at which you shut off the normal filtration operation and start backwashing. And that is either the turbidity is not meeting the standard or the pressure is the pressure required to push the water through the filter is too high. So it becomes very expensive, and sometimes the output is very poor. The amount coming out of the filter is very poor. So under those 2 conditions, you have to clean it. So A and B are shut down, and then we open C and D. Now D is connected to a wash water tank. Now this wash water is an elevated storage reservoir. So it's an elevated water storage reservoir which contains chlorinated water. Backwashing water is always chlorinated water. It comes in at very high speed. So the higher the elevation of the water, wash water, you get higher speed, higher velocity, higher pressure, and it comes in the reverse direction. So this is gravity flow and this is upflow. So the upflow is jet pressure, high velocity, and what we call fluidization of the bed happens at this point. Because of the high water velocity, you get complete. So this is a solid bed of sand. You can just imagine a glass and you put sand in it. It's a static bed. But the moment you have a jet of water, sometimes combined with air, There is no air valve that's shown over here. In general, in practice, we have two things. We have a high velocity jet of air and water. So the two together in the upflow mode will fluidize the entire bed. This entire thing becomes a slurry. And you can literally see it happen in the water treatment plants. And this slurry becomes, because it creates turbulent conditions, the sand grains literally rub against each other. First they collide and then they rub against each other and so on. And that friction between the sand grains is what is going to remove the clogged particles and the organic matter that has absorbed to the sand grains. Exactly. So those sand grains will now be free of the clogged material, and then they are allowed to settle. Okay. Now, these particles, after the jet velocities of air and water are stopped, this happens for a few minutes, not more than 5, 10, 15 minutes max. I don't think it goes on for more than that. So after this is done, and then the sand is allowed to settle back again, what you get is dirty water over here. So this dirty water is then collected, it's removed, the entire thing is drained. You get fresh, clean water coming in. Again, that is flushed out because it still contains quite a lot of dirt from this filter. And then after you get turbidity, again, after the filter is completely clean, so that dirty water is called wastewater or backwash water, and that is taken for either taken to the wastewater treatment plant or it's used for other purposes. Whatever it is, that is then after the backwashing. Now remember, the first flush has to be removed as well. And then you have the clean water starting to filter back in the gravity flow mode again. Okay, so this is backwashing. So backwashing is very frequent in rapid sand filters. Like I said, it's minimum, again, no, wrong. It can range from a few hours, like I said, even 2 hours of operation all the way to 24 hours. And it's never constant because it depends on the nature of the water quality. If the water quality is good, backwashing frequency can be 24 hours. If the water quality is poor, then backwashing frequency has to be much higher. So like I said, it can be 2 hours, 6 hours, whatever is appropriate to get good quality water. So backwashing is essential for regaining head loss due to clogging. And generally, we use chlorinated water. Okay. Then we come to the last process, and the last process is disinfection. So disinfection is the destruction or removal of vegetative pathogens. Vegetative means the ones that are capable of reproducing, and pathogens means disease-causing organisms. So we want pathogens that are reproducing to be thrown out of this water. So either we do it by chemical agents or we use physical methods for removing them. It is not equivalent to sterilization. In the lab, whatever we do, we normally sterilize equipment. When we are doing microbiological work in the medical facilities, in pathological labs, they sterilize their equipment. What we are doing is far from sterilizing the material. We are just trying to destroy vegetative pathogen. So it's a much milder process compared to sterilization. Sterilization is done by either autoclaving or membrane filtration. And then we have physical methods for doing this. It can be membrane filtration. We will go into that in the next class. And we have radiation. You can have UV radiation, X-rays, gamma rays, but for practical purposes, we use UV radiation. Chemical methods are basically where we have chemical disinfectants. You can have chlorinated compounds, chlorine, chloramine, chlorine dioxide. You can have ozone, and you can have potassium permanganate. So those of you who are from villages, you know that if you add potassium permanganate when you suspect that the microbial concentration is high, that is quite effective in controlling microbes, but it gives a pinkish color, pinkish purple color to water, and that is what people don't like. But in emergencies, most people recommend the use of potassium permanganate because it's non-toxic. Then we come to chlorine chemistry. So what happens when we add chlorine to water? So when we add chlorine to water, it results in the formation of two compounds, hypochlorous acid and hydrochloric acid. And there is a pKa associated with it. This hypochloric acid is not a stable compound. It's a highly unstable compound. It will dissociate into H plus and OCl minus. So this is hypochlorous acid. This is hypochlorite ion. And there is a pKa for it called, the pKa is 7.57. The hypochlorite ion then degrades into a mixture of chloride and chlorate. So OCl minus will further degrade to Cl minus and ClO3 minus. The standards require that there should be a free chlorine residual, that is minimum 0.2 milligrams per liter or 1 milligram if there is no better source. So if it is a good quality source, 0.2 is considered adequate, which I don't really find acceptable. And 1 milligram per liter is okay if there is no better source. There's something else I wanted to mention over here. Okay. So here we have the temperature. You know that the equilibrium constant will change if the temperature changes, but the change in temperature will result in a very small change in the speciation of HOCl and OCl minus. Now, if you take this particular reaction, HOCl going to H plus and OCl minus, so here we have pH on the x-axis and HOCl and OCl minus on the y-axis. So at 7.57, what will happen? At a pH of 7.57, what is the breakup between HOCl and OCl minus? The answer is 50%. So you can see, based on the equilibrium constant, you get equal amounts of HOCl and OCl minus. If the pH is 7, what is dominating? At pH 7, HOCl, the neutral ion, is dominant. So at 20 degrees centigrade, 80% of the chlorine applied is going to be in the form of HOCl. If the pH is 6, it goes up to more than 95%. Same thing on the other side. If the pH is 8, OCl minus dominates. If the pH is 9, again more of OCl will be formed. So what that tells us is, and there are other things, I don't know if I've included it, no. So we're not going to go into too many details because we don't have the time for it, but This is basically, this is about the equilibrium constant. You know that the reaction kinetics will also change as the temperature increases. So as the temperature increases, the rate of reaction is much faster. That's basically the Arrhenius effect of temperature on reaction kinetics, and that is another factor that will affect the efficiency of disinfection. At this point, I cannot show you, I won't go into the details about why HOCl is stronger, but you will have to accept the fact that HOCl, which is a neutral molecule, is a stronger and better disinfectant compared to OCl minus. The bacterial cell is also negatively charged. The outer surface of the bacterial or viral particle, they are all negatively charged, whether they are organic or inorganic. At pH 7, they are all negatively charged. And when everything is negatively charged, then obviously OCl minus cannot come close to the cell, and you get better results with HOCl, which is neutral. You have probably seen disinfection kinetics. The simplest law is what is called the Chick-Watson law. So the first one is 1908. It's called the Chick-Watson law. I'll come to the Watson part of it in a second. But the first one is Chick's law of disinfection. So dN by dt, N is the number of cells in bacterial cells in a particular sample. So the change in bacterial cells over a short period of time is proportionate to the population. And this is a first order reaction. This is the same thing as a first order reaction. When you integrate it, you get N is equal to N0 e to the power minus KT, minus because it's a decay plot. This K is assumed to be a constant. It's just a proportionality constant, but we know that if we change the cell concentration, disinfection concentration, temperature, pH, and several other factors, different species, all bacteria in the water will not behave in the same way. Some will die faster than the others. If you have virus particles versus bacteria, you won't get the same response. So all these things will have an impact on the K value. I also need to point out one more thing, and this is on the XY plot, you have the log value of the number of cells. These are normally what we do is plate counts. So I showed you plate counts in water pollution. And here what you have is the log of the surviving number of microbes, generally bacteria. So you can put it as log n. Instead of n, you can say log n, and you can say 0, 1, 2, 3, 4, and you get a straight line over time. So if you were to go from log 5 to log 4, then the time it takes to get one log decrease means from 10 to the power 5, you have gone to 10 to the power 4. So that's one log decrease. It's also called decimal reduction time, but it also means that 90% of the population has been destroyed. So only 10% of the total population is surviving. So that's why it's called decimal reduction time. So if I say I want 3 log removal, I have a starting population of 1 million cells, I want 3 log removal, which means my 1 million cells has to come down to 1,000 cells. So the question is how many minutes will be required to go down to 3 log removal, because that's my objective. Okay, so, and remember what I said about coliforms. Coliforms, we want 0 coliforms, because if coliforms are present, it means there's possible contamination of the water. So that's very important for you, all of you, to remember what is the meaning of 1 log decrease. 1 log decrease means 90% has gone, only 10% is surviving. One of the assumptions of Chick's law is that no matter what the starting concentration, so N0, no matter whether it is 1 million or 1,000 or 1 billion, it won't make any difference to K value. Okay, but this may or may not be true in practice. So like I said, I'm not going to go beyond this. There are several things we can continue to, which I can continue talking about, but there will be no end to this class if I do. So I will stop here for today and we will continue the remaining part of the topic in the next class. Okay. Any questions at this point? Questions, please. We have about 5 minutes, so I can take a few questions. No questions? Let me see if I can give you a problem. Okay, you can try problems 2 and 3. In fact, you can try all 5 of these problems. You've already gone through 1, so I will show you the remaining problems. You can try any of these. If you have an answer, let me know. Any answers to any of the questions? Are you all in a position to answer these questions?